Hello, today we're going to be talking about thermal energy. This can be found in sections 5.1 and 5.2 of our physical science textbook, and those are on pages 138 through 150. Clever. Temperature. First thing we're going to talk about with thermal energy is temperature. Temperature is a measurement of the kinetic energy of the particles of an object. We're not actually looking at what the heat or how much energy is there. We're just looking at a measurement. So there are lots of different temperature scales, and we'll get into that later on. But we're just measuring the kinetic energy. So remember, all matter is in motion. The faster your motion, the greater the kinetic energy. And even the table that you're sitting at right now, even though the solid matter, the state is solid, if we go down microscopically even farther down to the atomic level, even solids at an atomic level, the molecules in them are vibrating. And when you heat something up, those molecules vibrate faster and faster. And then once that happens, we transition between solid, liquids, and gas, as we looked back a long time ago at the different states of matter. And that's all in relative terms to the kinetic energy they have. And we can measure the kinetic energy by how hot it is. Think of, for example, an ice cube. So an ice cube is going to be 0 degrees Celsius because we know at 0 degrees Celsius, water is frozen. Not much kinetic energy in there because the movement of the molecules is confined because they're in a solid. But if we add some thermal energy, we warm those molecules up, they start moving and the ice melts into water. So anywhere between 0 and 100 degrees, the warmer it gets, the more faster those molecules are going to move. They have more kinetic energy because we're added energy. And eventually it'll start boiling, which is turning to a steam because the energy is now moving at a fast enough rate. The kinetic energy of those molecules will turn into and transition into steam. So what is thermal energy? Thermal energy is the sum of the kinetic and the potential energy of all the particles that make up an object. Most of the time when we're talking about thermal energy, we're talking about the kinetic part of that, which molecules are moving. But depending on how cold you go, or less hot, if we know that cold doesn't really exist, it's just a measure of thermal, how hot something is versus how not hot it is. We know that there are molecules that aren't moving very fast and they can move faster. So that's that measurement of the potential part of what they're moving. So for instance, we look at this house right here with a thermal imaging cam. We can see there are warm sections, which are your bright, and your cold sections are going to be the darker colors. And we can see the sum of all of the energy, the thermal energy, in that with using a thermal camera, which is really kind of cool, capturing the heat energy. Thermal energy depends on two factors. We have temperature and we have mass. When we stop and think about that, the greater the temperature you have, obviously, the greater the thermal energy you have. And on the flip side, the greater the mass, the greater the thermal energy. So if we have a 10-gram item and a 10-kilogram item, both made of the same material, we know that the thermal energy of that 10-kilogram item is going to be way more than that little 10-gram item. Because I add 1,000 joules of energy, I'm probably going to melt that 10-gram item, but the 10 kilograms has got enough mass, there's a lot of more atoms to it, which means I can add more heat to it overall. And that will be able to contain the heat and still shade the shape. All right. Also, I'll think of a hot water in a cup versus hot water in a pot. Hot water in a cup, while it's the same temperature, both are boiling, the thermal energy in the pot is much greater because there is much more water. Okay, that's what we talk about, the greater the mass. Which one takes longer to cool? Remember, cooling or reducing your heat is losing thermal energy. Remember, we did a lab where we had different substances, different cups made of different things with water inside of it. We put that in ice water and we watched the corresponding change to see whether that substance would cool off because of the insulating or conductive properties of the cup that it sat in. And so when it's cooling off, we know that the thermal energy is leaving, going to a lower level. So the hotter you are, the more energy you have, and energy always wants to go down to entropy, to a lower level. Okay? And obviously the cup, we know, takes less time to cool because there's not as much mass, which means it has lower thermal energy. Okay? Heat. Spend all this time talking about temperature. What is heat? Now remember, temperature and heat are two different things. Heat is energy that's transferred between two objects. We can measure heat in temperature, and we can also measure the transfer of heat in the form of energy. So there's two different ways you can measure heat. You can measure the energy that's transferred, and you can measure the kinetic energy that comes across as a temperature on the scale that we use. So heat is the energy that's transferred between objects due to a temperature difference. Remember, warmer objects always heat a cooler object because higher level of energy always seeks a lower level. So the hotter you are, the more energy that you're trying to get rid of. It's harder to hold on to that energy because everything around you is cooler. What is specific heat? Specific heat is when we talk about this whole measuring heat thing. It's the amount of heat it takes to raise the temperature of 1 kilogram of material 1 degree Celsius. That's one of the great things about the metric system, is the fact that all these things are kind of equivalent. So it's really easy. We don't have to do lots of conversions and none of that kind of stuff. We just know if we're going to raise 1 kilogram of material 1 degree Celsius, that is 1 unit of specific heat. Okay. Here are some comparisons of our specific heat. Now we notice that we have joules per kilogram in Celsius. Okay, so notice that's joules divided by kilograms, and then we have that times Celsius. 1 kilogram of material, 1 degree Celsius. So water, the specific heat of water is 4,200 versus iron, the specific heat is 450. Well, we know that it doesn't take very long to put an iron, something next to a fire, or like you're cooking marshmallows, and you get the metal rod, that little iron or steel rod, into the fire, it heats up red really, really fast. But if you were to take water and try to get water to boil off the fire, it'd take much longer. Why is that? Because it takes so much more energy to get that water to start increasing the degrees in Celsius, which is why water makes a really good insulator, because it tends to stay at a certain temperature. It takes a lot of energy to change the temperature. Again, water is very stable when it comes to transferring energy. So what heats faster? When we had that picture before of the water boiling in the pot, does the pot heat up faster or does the water heat up faster? Well, obviously the pot does, because it's made of metal, it's iron. So the specific heat is much less. So we know that the pot will get a lot hotter than the water. And here's that same picture again. Let's calculate thermal energy. How do we calculate thermal energy? Well, we can find the specific heat of a material by using a device called a calorimeter. And what a calorimeter does is it actually has this 1 kilogram of water with a thermometer in it. It's in the system that's locked and isolated, and then we burn, or we transfer that energy and see how much specific heat a specific item has. And we can also use that and turn it into calories instead of joules, which is why it's called a calorimeter. And they know how many calories a certain food item has, because some of those items have been done in a calorimeter to find out how much energy you would get if you ate that. Here is the formula. It's Q, which is the thermal energy in joules, is equal to the mass times the specific heat times the change in temperature. All right, let's talk about transferring thermal energy. How is thermal energy transferred from one object to another? There are 3 different ways we do that. We have conduction, convection, and radiation. I'm going to break each one of those down. We've done a lab on conduction. That was when we had the different cups in the ice water. We've done convection, and that is studying through fluid. We did that lab on that as well, as we watched the water swirling the pepper, also the candle smoke curling in the air. And then there's radiation. So again, in a pot, you actually have all 3 when you're boiling and have a pot over water. If you feel the heat radiating off of the burner pad, that's the radiation. All right, convection is the water cycling in there, and then the pot is actually on the fire, on the heating part of it, and that conducts the heat. There's lots of different, all 3 can be seen in a simple example like that. So what is conduction? Conduction is the transfer of thermal energy by collisions between the particles that make up the matter. When we stop and think about that, the more dense you are, the more dense your matter, the more solid state you are, the easier, the more conductive you tend to be. Air is a very poor conductor because the molecules in the air are very far apart. It takes time for them to actually collide and bounce off and transfer that heat, which is why we say air is a poor conductor, but a very good insulator. So conduction, again, is that transfer. And this explains how heat travels in the object, why you can hold the pot handle at the very end down here and not feel the heat, but if you grab it really close to the pot, it is hotter. Same thing like a spoon. When you're stirring something very hot, heat will travel up the spoon. And here shows a little example of that travel. If you have a candle on a bar, We can watch the travel of heat as the heat moves through that particular object. Thermal conductors. Uh, this is a material which transfers thermal energy the best, and we a lot of times just call them conductors because conductors that are good thermal conductors also tend to be good conductors of electrical energy as well. The material in which the electrons are not bound to the individual atoms. So what happens is they just kind of bounce from one to the other. They just take that energy with them. Metals are the best known thermal conductors. The other type of transfer of energy we talked about is convection. Convection is the transfer of thermal energy in a fluid. And what happens is we have this movement of fluids, both air and liquid. Remember, air and liquid are both fluids. The warmer something is, the more dense, the less dense it gets because the space between the molecules gets farther apart because of the vibrating energy. The more energy they have, the faster they vibrate, the farther they get spread out, which means they have less density, which means they float. That's why heat, hot air, always goes to the top of the room, and the cold air, the more dense air, stays closer to the floor. And that movement is called convection by warmer and cooler fluids. Lava lamps are a perfect example of convection. The heat source is down low. Once the wax absorbs that heat, it becomes less dense and it blobs and morphs up to the very top. As it's at the top, it cools down, and then because it's cooler and less dense, it falls down. Great examples of convection. Warmer fluids are less dense, as I said, and cooler fluids are more dense. Convection currents also explain weather conditions. We think about the Earth's atmosphere as actually a fluid made of various gases, and that thermal energy from the equator then rises up into the air and then floats over, and we have this cycle, which is why on both sides of the rainforest zones there tend to be deserts, both in Africa, Europe area, also in South America, because of the warm, cooler, dry air that falls. As the warm, moist air rises, it has to lose the moisture, so it drops lots of rain in that area. And then over here also shows, again, a great one that shows all the different cycles that happen because of the convection currents. It's really kind of interesting when you study some of that stuff in ecology and later on in other sciences, in earth science. Radiation, the last of the transfers of energies, this is done by the transferring energy by electromagnetic waves. Lights are radiant, all right, that's radiation. Microwaves also heat things up. So when radiation strikes a material, the material warms, but not the air in between, which is why when you open up the microwave, if you have a tightly sealed container, the air in the microwave isn't warm at all. It's just whatever you've been warming up, that is hot. We also have radiative heaters, heaters that have a radiation heater. There we go. A radiation heater. It's the air isn't warming at all, but you feel warmer because you're sitting in front of that type of heater. Radiation transfers thermal energy through the spaces between the particles. Gases transform this form of energy more rapidly and efficiently than solids and liquids because there's less stuff in the way of that radiation, which is why if you want to, when you think about when you're standing next to a very, very hot fire, the front of you gets very, very hot. But if you want to block that, you just hold a blanket in front of you, and that blocks most of the heat radiating off of that fire. When you stop and think about it, the blanket should actually make you feel warmer. Why does it help you feel cooler? It's because you're blocking that radiative barrier with the solid. How do you control heat? Objects, living and non, constantly lose heat to their surroundings. Remember, hot objects want to constantly send that energy out to a cooler or less hot environment. Animals have lots of special features that control the loss of this thermal energy. The differences between the Antarctic seal, the emperor penguin, the shiny lizards. There's furs and feathers. There's layers of fat. There's even different colors to help with the radiative energy gain. There's behaviors during a hot day. They'll sleep in the shade somewhere, and they'll come out at night when it's much cooler. Things of that nature. Thermal insulators, a material through which thermal energy moves slowly. So we talked about conductive, where it moves quickly, and insulator, and insulation is something that thermal energy moves very slowly. All right, and that's the end of the slideshow. Thank you very much.